Hello and welcome everyone. My name is Peter Robinson and this is the Ethereum Engineering Group Meetup. Today we've got Daniel here who's going to talk about smart contracts and provable smart contracts. And so before you get into your talk, Daniel, and present your slides, can you tell us a little bit about yourself?
Yeah, sure. So my name is Daniel Britton and I'm a current PhD student at the University of Waikato in Hamilton, and I live in New Zealand. And my research involves, trying to prove properties about smart contracts, which I'll get into. But yeah, I enjoy going for runs and just having a good time with friends and family as well.
Sounds great. And so I think earlier, just before we were talking, and you said you were in the midst of finishing your PhD, but you also don't currently have a role lined up. So anyone who's watching here live or watching on YouTube, reach out to Daniel. What's the best way for people to reach out? Should they section request on LinkedIn? Is that a good idea?
Yeah, I think LinkedIn is probably the best place to get in touch. Yeah, I will be submitting my thesis in about 5 or 6 months, and I'm looking for opportunities after that.
Okay, awesome. All right. Well, good luck with your PhD and then with your job hunt. All right. So look, please share your slides and do your talk. Yeah.
There you go. All righty. Hi there. So as I mentioned, I'm Daniel Britton, and I'll be presenting on provably correct smart contracts using DeepSEA. And this work is a bit of research of my own, built upon a whole host of research and work done by Certic, which is a company that I've been collaborating with. So first of all, I'll give an overall goal of this talk, which is to demonstrate a technique for showing the correctness of smart contracts. And in particular, I'm after a technique that is provably backed. So it is brilliant and important to do tests to verify contracts to a certain level, but to go to the next level to ensure that even some unforeseen errors don't occur, provable correctness is really important. And so I'll be talking about the technique of theorem proving using the proof assistant COC. So this is an overview of my talk. So first of all, I'll discuss an example of proving something unrelated to the blockchain in the proof assistant COC. And then I'll discuss a DeepSEA example. So DeepSEA stands for Deep Simulation of Executable Abstractions. And this involves compiling a source language into the target language and then doing a process called refinement down to the Ethereum virtual machine bytecode. And then I'll talk about a proof via example of a simpler proof that we can all follow in DeepSEA. And then I'll discuss the crowdfunding property of a correctness property of a crowdfunding contract, which has appeared in some papers that I have written. And lastly, I'll give a few paper overviews if people are interested in reading further in this area. So first of all, this is intended to be an example that is fairly easy to follow compared to other proofs in COC. And so the example is to do with even and odd numbers. So I'm going to dive right in. So this here is the setup and the proof of the lemma that says for all natural numbers, if that natural number is even, then n plus 1, that number plus 1, is odd. This intuitively seems true, I'm sure, to all of us. But if we look carefully, we have to actually show this not to prove to another human, but to prove it to the computer. So the definition of even is given here. So it's a number n is even if there exists a number k such that that number n is 2 times this other number k. So we have to provide a number k that when times by 2 equals n. And similarly for odd, there exists a number L such that the number we were wondering about, n, equals 2 times L plus 1. And this is very similar to the mathematical definition of even and odd that you would find in an introductory math textbook. So what we have now is the way that proofs are done in the Coq proof assistant. So what we have is we have the lemma statement, so is given first, and when I click on it, it shows what we would see in the Coq IDE. So here we have the goal, so that is what we are trying to prove. And if you look carefully, you'll see that there is a line, just a horizontal line. And so everything above that line is things that we already know. So when we start our proof, we have to try to prove the goal based upon typically nothing, but sometimes there are things in the context. And then what we can do is we can do proof commands. So proof commands are called tactics, and these progress the proof step by step by step. So first of all, we can do the intros command, which stands for introduction. And so this introduces the things that can be lifted to hypotheses. So for example, we had for all nat, so we had a number n. So what we do is we introduce an arbitrary n, which has no other constraints on it, and this becomes above the line and replaces the for all n nat. So because it's arbitrary, it's essentially the same as saying, okay, we just pick an arbitrary number. So it's the same as saying, like, this number could be any number. So if we prove it with this number that could be any number, we've proven it for all numbers. And we also lift the even n to knowledge that's called a hypothesis, which is why it's given the letter H. All right, so now we've got to try from n and the fact that it's even to prove that n plus 1 is odd. And so if we unfold now, so unfold means we take the kind of short definition. So in this case, we take even and we essentially replace it with its body, which is exists k n equals 2 plus k. So when we do that, we see that the even that we had over here is replaced with exists k nat. So nat stands for natural number, such that n equals 2 times k. All right. So now moving on to this next command, which, so when we have in Coq, when we have something of type exists something, what this means is it holds the kind of knowledge in a way that we can destructure into splitting the exists into a concrete number. So we had said, okay, there exists a k, so let's actually get that k. So this is what destruct does. It destructures. So now we have that k as a concrete natural number, and we know that n equals 2 times k for that concrete natural number. And we're almost there. So now we're going to unfold odd, which is the exact same as we did with unfolding even earlier. And this replaces odd with its definition from the top, which is there. All right. So now we want to prove that there exists some number L that n plus 1 equals 2 times L plus 1. So it so happens that we have a number, if we think about it carefully. So if we look carefully, we can see that we have n equals 2 times k. And if we were to use 2 times k, if we were to use k for L, we would have 2 times k plus 1. And 2 times k equals n. So the 2 times k will be replaced with n plus 1 over here. And then we'll have n plus 1 equals n plus 1. So this is kind of the step that technically involves some insight into what's going on by picking. So it's picking what goes in for the exists. So we say exists k, by what this means is that it's different to this exists. This is a command, and this command says for that L, I'm going to put in the K. And so once we do that, the L is replaced by the K. And we could have said exists 42, and then we would have just got stuck in the proof because we wouldn't have been able to prove that n plus 1 equals 2 times 42 plus 1. But we chose wisely, we chose K. And so now we can see that we're almost there. So n equals 2 times K. We know this. And so we want to rewrite 2 times K into n, which we can do using rewrite left arrow H, or we could use automation here. And over here, now we have rewritten the 2 times K into an n. And so we have n plus 1 equals n plus 1, which I hope everyone can see is very true. And so the command that resolves this is just reflexivity, which shows that n plus 1 equals n plus 1 is like propositionally true. All right, so this gives us an overview of what it looks like to do a proof in Coq. And the key things to remember are that there's this line where you have the goals on the bottom and your hypotheses on the top. And you're always trying to prove the bottom based upon what you have in the context on the top. And you do so by typing different commands that manipulate the goal and the hypotheses. Yeah. So now I'll move on to the next thing, which is DeepSEA. So DeepSEA is first of all, it's a programming language, but it's more like a framework and a system for doing proofs about smart contracts using the Coq proof assistant as its base. And so DeepSEA is a language, and it's got a syntax that you'll see shortly, but the syntax isn't too important. It would be possible to change the syntax in the future to look a bit more like Solidity. But for now, it is as it is. And so DeepSEA, what it does is it takes your contract that you write, and it generates a proof that the high-level representation is so that the low-level representation refines the high-level representation. So in other words, that the bytecode on the blockchain will behave exactly as any proofs done about the high-level version as well. So to give you a taste of what this is like, I'm going to discuss a trivial contract converting a Boolean to an integer. And then I'll discuss later on some work that I've done to do with a crowdfunding smart contract, which is less trivial. So this is a DeepSEA contract. So this is the full contract. There's nothing missing here. So this is an example. So we could have we have like signatures for the functions. So this contract here is very trivial because it doesn't have any storage. It simply has one function called bool to int, which in fact is a constant function, as in it doesn't affect storage at all. And so it will take the input b, and if b is true, then it will return 1, otherwise it will return 0. And we also have a layering system in DeepSEA. And what this allows you to do is have different contracts layered on top of each other in ways such that they can kind of, yeah, it's useful for proofs sometimes, and can manage their interactions with each other. So we'll bear this in mind, and I'll add one function to it later. Actually, I'll add one function to it right now, sorry. Now we'll add one extra function just to make it more interesting. So this is called bool to int tracker, which is essentially the same as bool to int, except that this bool to int tracker, there's a storage variable called seen true yet, which initially starts out as false. And then seen true yet, if the bool to int tracker function gets past true, it will record seen true yet as true, and then return still 1 as before, and otherwise return 0. And this just allows us to see a bit more of what DeepSEA is doing in the next slides. So they're two identical functions, but the boolean tracker keeps track of when it's seen true. So as you'd expect from a compiler, we can generate bytecode, and this is how you would do it using the DeepSEA compiler. And yeah, I should point out at this point that before diving in too much into DeepSEA, I would highly recommend reading their license terms. The current terms are primarily or pretty much exclusively an SE BY license, as far as I understand, for academic use only, so or evaluation. But just read their license first before you dive in too much because you're so excited about it. Yeah, and this is their ADI, so the binary interface. So we can see that we've got 3 functions. We have the bool2int, which we defined, bool2int tracker, which we also defined, and we also have constructor, which is used when the contract is deployed onto the blockchain. And you can define your own constructor simply by calling it constructor to customize what happens here. The other thing to point out is that it also generates the state mutability of view or payable. And yeah, but anyway, it's an ABI, it works. There we go. So now just coming back to the contract before we dive into how this gets converted into COC. So the way I think about this in DeepSEA is that this entire DeepSEA definition is not a kind of authoritative view of what the contract is doing. This is sort of like a shorthand language for writing what gets loaded in as by the COC proof assistant. So when we write, so DeepSEA compile to COC, what this does is it gives us what I consider the authoritative version of the contract. And the reason I say this is because there's the high-level version in COC with a proof that it correlates to the low-level version of the bytecode, but there's no particular proof necessarily that this code, which is written in its kind of DeepSEA language, this is not necessarily considered part of that chain of proof. So it's much better to consider the actual version in COC as authoritative. And that's the version that you do the proofs on, and so it's perfectly fine to do that. So this is what you get when you look at the first function bool2int. It essentially looks like if, then return 1, else return 0. And I'll just show you what it looks like literally in the proof assistant, which is here. So you see that here is what I copied up there. And everything else is a bit of boilerplate to do with the machine environment and the memory model ops. And but we have a function essentially that takes an input of f, and if it is true, then it will return 1, else 0, as we expect. Now, the thing that you can't quite see so much here is that there is like the return 1, you can see, if you might be familiar with functional programming languages that use monads, this is evidence of that. But yeah, we'll mention that more in the next slide. The point here is that this is the COC version that gets generated that is quite similar to what we saw on this slide here. It's very easy to see the correspondence. But it also generates lower level versions of the same function. Kind of one level down is this representation here. And so this is in like as a command constructor of if then else, and it will either return 1 or 0, depending upon the variable over here. And so this allows us to, this just is a glimpse rather of the steps that you can go down, down, down into all the way down to bytecode. And unfortunately, I can't show the proofs. But yeah, I'm hoping that will change in the future. And this is just a glimpse of what that looks like. So now we move on to the DSC trivial.ds cop. So for bool to int tracker. So this is the one with the tracker. And this is what this one looks like. So we have very similar to before, but we have this additional command squeezed in, which is that it'll modify the seen true yet variable to true. And what this does here is allows us to see that our so our seen true yet set into true is being reflected in the code. And as before, the generated code, as before, the monads that modify as is reflected in the literal code that coq generates. And I'll also note these double semicolon is kind of like the semicolon in a imperative language, but this is all wrapped up in the state monad that is used to link commands together. And we'll see that also evidence of that as well in the one level down. We have an if then else branching on a variable with a sequence of commands, which is cc store. So cc store involves storing a value into the storage of the contract, and then it'll also still yield 1 in the true branch and 0 in the false branch. Okay, so this gives an idea that DeepSEA generates bytecode, generates an ABI, and it generates a coq representation of the function. And the coq representation gets compiled down to bytecode. So the bytecode generation is actually done via extracting from coq certain parts of the coq code base that help with the extraction. And it might be possible to do this entire tool chain within coq as well. All right, so now I'm going to move on to a proof about our contract. And so the point of this proof is to demonstrate what it looks like, not just to do an arbitrary proof in coq, but to do one embedded in the DeepSEA system. So this is going to be what we're going to try and prove. It's still a fairly straightforward proof, but it's unfortunately these things end up being slightly harder than one expects a lot of the time. But this one's not too bad. So I'll just introduce you to some of the syntax here. So first of all, there's the input. So that is the Boolean of true or false that gets passed into the function. So bool to int opt takes input, which is the Boolean that it flips to return either 1 or 0 on. Context is kind of like the call context. So it includes the call value, the caller's address, and a few other properties related to the call. And so if someone was sending money in, this could handle the recording of that money. And the before is the state of the contract beforehand. And the result is the return value of executing the contract. And after is the state of the contract afterwards. Machine environment, you can basically ignore, but it kind of wraps up some of the details into a single variable that's used, that's required to make the function know what it's doing. In particular, it wraps up, in particular, it wraps up the before and the context and the contract address. And so essentially it just wraps it up into a single variable so that we're not listing too many variables all the time. Now run state T stands for run state transformer. And so this will is a very important function that will execute a program on a particular state. So it executes a smart contract function on a particular state. So we have the function over here, which is bool to int opt with that input and that machine environment. And we have the contract state before, which is the state of the contract before it is run. And so the result is, as I said, the return value, and after is the contract state after. So we say, okay, let's assume that when we run the contract, it returns some result and a after value for its contract storage. If we assume that, then the result should be 1 if and only if the input is true. So this is could be considered the correctness property for that particular contract function. So the result must be 1 exactly when the input is true. All right, so now let's prove it. Cool. So the main goal that we're trying to prove is as before, the result is 1 if and only if the input is true. So if we look at the proof, we have this contract address in the context, and then we have, it looks a bit complicated, but it's exactly what we had on the previous slide, just as essentially this section here. So all of this is what we're trying to prove. So the first thing we can do is intros. So we see here, this is very common in proofs to just do intros first. And we see we're trying to prove the result is 1 if and only if the input is true. And most crucially, we have the knowledge that running the contract gives this, the result and after, based upon the input. And so as before, we want to unfold. So remember, we unfolded even and odd. So we can unfold bool to int. And when we do that, so beforehand, it looked a bit like this. By the way, I have hidden some hypotheses on this slide just to make it easier to read. So here we had trivial bool to int opt. And after we unfold it, we simply have if input, then return 1, else return 0. Which is much easier to deal with. And so what we're going to do now is we're going to split the goal. So we've got left hand implies right hand side and right hand implies left hand side, and we'll prove each of those directions one at a time. So first of all, we'll prove that the left hand side implies the right hand side. So we assume that the result is 1, and we're trying to prove that the input is true. And we know that the program will run as described by the hypothesis. So what we do now is one of the most useful parts of the DeepSEA system. It's this tactic that is provided called inv run state T branching, which stands for inversion of run state T with branching. So inversion of run state T with branching, what it will do is it will look at our run state T kind of body, and it will automatically split based upon things like an if statement, and it will just handle the complexities with run state T as well. And so mainly it's going to split down, one branch will go down the true branch, and then one branch will go down the false branch. And so we're kind of exploring, if you think of code, like code coverage, this is a little bit like that. So it's covering the left-hand branch and the right-hand branch. And so when we go down the true branch, so this branch here, it infers, so it does some inference for us. So it infers that the input must be true because that's how it got to the true branch. And it calculates that the return value or result must be 1. So we know that input is true and result is 1. And because of this, the goal previously was input equals true, right? And so it's automatically substituted in this one here for us. So it's substituted input for true. And so we've got true equals true. So that's trivially true, as we can see. And so we solve it by reflexivity or auto. And now we'll go down the false branch. Now, the problem with the false branch is that if we go down the false branch, input must be false, because to get to the false branch, we must have had that input as false. But we assumed that input was true. We assumed that, sorry, my bad. We backtrack a bit. So if input is, if we go on the false branch, then we must have returned 0. But remember, we assumed that the result is 1. So we have 0 equals result, and result is 1. So this gives us a contradiction because 1 does not equal 0. And we can substitute to see this clearly. 0 equals 1. And then there's a tactic called discriminate, which handles the situation for us. And so now we do a very similar thing for the second branch. So if we go down, so now we are assuming that the input is true and trying to show that the result is 1. So if we go down the true branch, then the true branch has that the result is 1. So we can gather that information from running the code essentially. And now we have that result is 1 is our goal, and our hypothesis is that 1 equals result. And so again, we can substitute and we see that 1 equals 1, which is clear from reflexivity. All right, so now I will do the last bullet point, which is going down the false branch of this statement when we are assuming that the input is true and we're trying to prove the result is 1. So if we go down the false branch, that means that the result is that means that the input value, so if we're going down the false branch, then input must have been false. But the thing is that, so we've got input equals false here, but we assumed that that the input is true, and so we end up with this contradiction here: false equals true. And so as a result, we can use discriminate to say, okay, false doesn't equal true. This branch of reasoning is impossible, and that gives us our last case. And so now we can write QED, and that checks that we've done everything and haven't missed anything. And that's the full proof of this lemma here. And so I'll just point out that this lemma here is a proof about like an individual smart contract function. It's not, it doesn't take into account the contract as a whole, but there are ways which I'll discuss later for doing that. And the next thing to point out is that our bool to int tracker, so that was a proof about bool to int, and the proof for bool to int tracker is it's actually identical. Nothing changes because the automation in run state T branching can handle the situation just fine. But we do notice that there are some differences. In our run state T, there's a monad state update for the difference between the tracker, for it to track that it's seen true yet. But we also get some other information that's quite interesting. So automatically in the false branch, so in the false branch, we don't change any storage variables at all. So in the false branch, we also get this hypothesis visible that says contract state before equals after, which shows us nothing has changed. And it's great that the DeepSEA system provides this knowledge to us, because if we were reasoning about a complex contract that sometimes didn't change the storage, that would be very useful. So yeah, that's the bulletin tracker. I'd like to just pause for a moment here and just invite any questions we have at this stage. So if anyone has a question, feel free to ask.
Daniel, yeah, one of the things that I feel like might be a bit confusing is that you talked about the contract executing and producing a result, but you didn't talk about, you know, the situations where it might not produce a result. You kind of assumed that it did produce a result, you know, like it could have run out of gas or something else might have happened.
Yes, yeah, that's definitely, yeah. That's a good point. So in this case here, the lemma explicitly assumes that it returns some result. And so if the contract runs out of gas, or the contract, I mean, this contract wouldn't fail because it can't, but if it did fail for some reason, then this proof is kind of saying nothing because it assumes it succeeds. And so when you're doing proofs more carefully, the way, so one of my papers, which I 16 was going to discuss later, this paper, what it does is it talks about how we model the kind of the whole contract and as well as the blockchain, including failure states, so that when there's a case where it might run out of gas or something, it's modeled. But typically the easiest way that this is done is just if it's going to revert. So, and a lot of the time the properties we're interested in are to do with reachable states. And so if a contract reverts, it doesn't really make much difference. But that is still different for something like liveness properties, which are still, yeah, you can do some things in DeepSEA to handle that, but it's not perfect. Yeah. Any other questions or comments again?
Yeah, I have a question. Most of the things you're doing can be done with any other proof assistant like Lean or Isabelle and so on. So is there anything specific that you use in Coq that, or anyway, why did you choose Coq?
Yeah, great question. I think that probably the main practical reason is that, so the what I'm showing here is a lot of the surface level proofs, but there is a whole lot of proofs like to do with this kind of content here, in terms of the correctness of each function down to bytecode. And that whole project was in Coq. So to recapitulate that whole project in another proof assistant would have been a lot of effort. So the main thing is the existing code base was in Coq. Yeah.
So I was asking this question because in Lean, for instance, you can write DSLs. And this is somehow similar to what you are showing at the beginning. You've got some high-level code that you compile down into Coq, and you say that's the reference code. Actually, the top-level one, I don't really care. It's the Coq version that should be used, so you can do that in Lean, I think, now.
I'm sorry, I'm not sure I follow. Could you mind repeating the question, please?
So there are a few things in other theorem provers like Lean that you could use as well. For instance, writing a DSL. That's what you have in your DeepSEA language, right? It's a high-level language to write contracts that you compile down into Coq.
Yeah.
So there are mechanisms to do that in Lean, I know. So that could be also
Interesting.
an advantage. Yeah.
Yeah, I mean, I haven't particularly looked into that.
But that's a good reason to choose the code, because you have a lot of existing components and you can focus on something.
Yeah,
Different. Yeah, that's good.
yeah. No, I'm curious about what Lean can do. Yeah, I think yeah, I think I mean, there is a difference between a compiler and a verified compiler, and so I'm not sure whether what Lean can do automatically generates like proofs with refinement proofs, but I'd be interested to look into that. Thank you. Yeah.
I don't want to delay too much, but I do have a question that's actually based on David's question.
Yeah.
So he was talking about, like if something reverted, so you had a transaction function and it reverted, and then you sort of said, oh, look, but it doesn't really matter too much. But wouldn't you want to formally verify that if you do this, it does revert? And so it does, I mean, so because even when something reverts, it does return a value, but the value is the function selector. I mean, it says error, and here's the function selector and the parameters of the code. So it normally with revert, it's capital E for error and then bracket string. So it does return something, but do you understand what I'm getting at?
Yes, no, totally. Yeah, no, and this is flexible enough to do that. For example, if we had like, for example, if we had over here, if B, then 1, else fail, then this obviously would fail every time it got false. And then in our proof, we could want to say prove that every time it got 0, it would fail. So we wouldn't say this part of the lemma. We would just say run state t of, and then input, if we put false there, sorry, it should equal none. And that's what we could do. We could say, okay, we're proving that if we get a input of false, we will revert. Yeah, so that is possible. And obviously this example is meant to be a toy example, but this would scale to more complex situations. Yeah.
Thank you.
All right, I'll move on for now, but feel free to hold questions to the end as well. So now, crowdfunding correctness property. So this is a crowdfunding contract. So if you think of Kickstarter or the likes, where people can donate money, and then what they can do is, if the goal is met, the person who set up the fund within the time can retrieve all the money, and otherwise the money is returned or able to be returned to the donors. And so the property that I want to talk about is a property that is like one part of a correctness proof for a crowdfunding contract. And the idea here is that once you have donated money, then that record of donation, so that storage field in the smart contract stays untouched unless you withdraw money yourself and kind of make that record go away. So the complexities here are that this proof involves looking over a trace of the contract over time and properties about that trace, and then proving properties. And this also has the full complexity of the paper I'll talk about later, which models the smart contract and blockchain as a whole, in terms of all of the smart contract functions together are considered, which is critical for this kind of situation, because if you had one smart contract function that recorded the donations and then a different smart contract function that just deleted a donation record, that would be problematic for this correctness proof. So first of all, just to introduce a sort of, it's kind of like a temporal logic style predicate. So we have this notion, which is based upon a paper by Ilya Sergey and others as part of their Scylla papers. And so this is called since as long. And so we have over here is we have the main things to grasp initially are, so we have a predicate that says, okay, reachable via. So we have a start state, a finish state, and some actions. So imagine you start at the start, and then you take the list of actions, and then you end up in finish. That's sort of what this guarantees. So we assume that we have a start, a finish, and a list of actions. And then we assume that some property 1, holds for start. And then we assume that property about action holds for everything in the list of actions. So for every act in the list of actions, we have some property about that action holding. And then if that's the case, so if we have property 1 and property about actions, then property 2 must hold about the final state. So you can think of this as like, okay, in our final state, we want some property. And if we have that property way back somewhere in the start and for every state in between, then we're good. We have that property. And that's what this idea is, the idea that this is expressing. And so we can write this as like we have property 2 since property 1 occurred, as long as property about action occurred all the way through. So this is what it looks like in an example, which might make things clearer. So, so we have property 2, which is that the donation is recorded about the user and the amount, since it was essentially first recorded about the user and the amount, as long as we have had no claims from the user. And so this is the full theorem that captures this donation preservation of the donation record. Cool. And so now I will just touch on the proof. So this is what it looks like. I am not going to go into detail of this one, but I'll try to go through it slowly so you can get a feel for its length. It does actually fit on one slide if you squish it up. But yeah, so this proof here, I just had some notes. So if you see here, it gets complicated, but there are some similarities to what we've done before. We have a run state transformer, and we have a crowdfunding donate op, which used to be trivial bool to int opt. And then what we do is we unfold it, just like we were unfolding things earlier. And now that crowdfunding donate opt section gets replaced by the content of the crowdfunding function, which, as you can see, is, I mean, it's a bit long, but it's still quite short. But yeah, it's doing things like, it's got the semicolons we saw earlier. It's returning items at certain points, and like there. And so basically the point here is that the basic ingredients of the proof is the same. And to get an idea of what's going on as well, we can see that in this last one here, we have the crowdfunding get funds, and get funds. So get funds is the one for the owner to get the funds back when the deadline has passed. And so the get funds here is independent of the donation record, because once the deadline has passed, the donor's record doesn't matter anymore. And so the get funds here is, in theory, a really easy proof, and in practice, it is an easy proof as well. So this is the same as run state T, the run in state T branching that I talked about before. And there's a short sequence of commands that solve every single goal. So this may look complicated, but actually in 4 commands over here, it is solved by basically because it's irrelevant. Everything that happens in that function is irrelevant to the lemma we're proving. So that just gives a vague glimpse. I'm happy to talk more about this, but I'll move on for now. But yeah, that just gives a glimpse of this theorem here, which is quite nice because temporal logic type predicates tend to be harder. Like there are less systems out there that can handle this kind of a predicate. I think there are some, but not many. All right, so now I'll start wrapping up, but I'd like to just give a brief overview of some papers which you might be interested in reading and talk about some of that content. So firstly, there's a paper about modeling a blockchain for smart contract verification using DeepSEA. This was presented at FTSES last year at the Splash conference. And yeah, the idea behind this paper is that we're trying to take those individual smart contract functions and wrap them together into a cohesive whole, and then also add a bit of machinery to model properties of the blockchain around that as well. And the whole point of this is to make it more practical to create these trustworthy standards using what many consider the gold standard of formal methods. And yeah, so if you're interested in getting an overview of what the modeling of a blockchain looks like as it kind of integrates with DeepSEA, then I'd recommend checking out this paper. This paper is is actually an extended abstract of a poster. And so the point of this is to just give an overview of the whole of DeepSEA. So if you want a broad strokes overview of DeepSEA in general, then this is a great place. It's just 2 pages. And this was a paper I wrote a couple of years back, which involved handling reentrancy in DeepSEA. So something I haven't talked about at all is that reentrancy is a massive issue. If you think of the DAO and many others, it's important to get reentrancy right. And so in this paper, I discuss how DeepSEA can handle reentrancy. And basically, I enforce, as it says there, the checks effects interactions pattern. So it does limit the types of contracts you can write a bit, but it does make it safe. So the trade-off. And lastly, this is not my paper, but it's by a collaborator, Canary and Wilhelm and Xinhuan, and they have done some really interesting work to do with automated market makers and trying to show that there's lower bounds on price manipulation, so that certain contracts similar to Uniswap cannot be manipulated too much, and it shows that the price of manipulation is so high that in certain contexts that it would be unlikely that people would try to manipulate them. Yeah, early stage work, but still very interesting. Yeah. And lastly, unfortunately, we don't have a DeepSEA for blockchain paper just yet, but watch this space over the next year or so. But there is a DeepSEA paper about the version for the C programming language. So much of the concepts are very similar. So if you'd like to get a kind of detailed view of the C programming language version of DeepSEA, then this would be worth a look. And yeah, that's all. So I would like to have a shout out to Electreon, which is the company, the product that made these slides possible. So it's an open source project, really cool. And there are some links there available at the link that I believe Peter will post to these slides. And I would also just like to thank my professor, my supervisor, Professor Steve Reeves at the University of Waikato, and also Wilhelm Scherberg at CERTIC, because they've given so much valuable insight and input. And also Jingsun at University of Auckland for kindly hosting me. So thank you very much.
Thank you. Thank you. Yes. So why don't we go through that? There are some questions in the chat. Why don't we hit the questions in the chat first? And I can see, Frank, you've got a question just there. Why don't you, do you want to ask that directly, or shall I read it out?
Yeah, that was not that important in the profit. Sorry, there's a plane. In the proof of yeah, sorry. In the proof about reachability, you assume that there is a transition function somewhere, right? The run state is a transition function, so you have it written down.
Yes, yeah. So there's in fact a specific function that I didn't include. Well, technically it's in the slides, but it's hidden, called step, which is how transition function. Yeah.
So I've got a question related to the practicality of the approach. So you showed some proof for a small contract. It's quite a lot of lines of proofs. So do you think it's practical? Do you have any idea of the sizes of the proofs compared to the sizes of the, let's say, the contract? And if it's not practical yet, what do you think we have to do to make it more practical?
That's a very good question. Definitely needs work to become more practical. Definitely. I think probably so one thing is that there are also, like, probably the biggest kind of competitor for DeepSEA in general is things that use SMT solvers as part of their tool chain somehow. Yeah, so those might, like, but there's trade-offs, because sometimes when you're using an SMT solver and it fails, like, you don't really know why, like, it's a bit confusing. And maybe it's a problem with the SMT solver, maybe it's your particular setup. But then in something like theorem proving, like pure theorem proving with a bit of automation, like I've shown, sometimes things are just very, very tedious, and you pretty much know where you're at in terms of why things are working or not most of the time. But it's very tedious because you're sometimes proving things and showing things that are just really obvious. I don't know. I wonder whether tools like, not now, but in the future, tools like GitHub Copilot or something like that might kind of merge the two fields in some sense. But yeah, no, I think the practicality is a big problem, because these proofs take me a long time, and probably more than most companies would be willing to spend, even for the extra certainty. But I think the more we do it, the more examples other people will have, and even like machine learning will have to figure out quicker ways to get through it. Yeah, it's really neat when you do a proof in a theorem prover, because you really feel like you've captured quite clearly what makes it correct, and the why. The why seems embedded in code. But as to that being practical for business, I think we're still, making progress. And I think the best thing would be more machine learning integration. Yeah. Thanks for the question.
Yeah. There's another question in the chat. Are you familiar with Certora? It's a language CVL, is much simpler. Any comments on that?
The name vaguely rings a bell. Oops. Yeah, I'm trying to remember them. Yeah, I've definitely heard of them before, but I can't remember the details. So I can't comment. But Certora analyzes EVM bytecode. Okay, yeah. So for me, in my PhD thesis, my focus was very much, yes, okay, I vaguely remember Certora now. So my main focus was on analyzing high-level specifications, because I find it a bit more interesting personally than analyzing bytecode. And also I find it quite neat to consider the link between high-level specs and low-level bytecode. So just analyzing bytecode for me is a very interesting research area, I'm sure, for some people. But me personally, I was more interested in something that I could prove properties about a high-level representation. But yeah, Certora is probably a great example of something. And you analyze EVM bytecode, you have the advantage of being able to analyze at scale. You can just pull contracts off the network and analyze them. But you can't, you kind of can't. There's some things that are harder to do than when you have code that is much closer to the programmer's intentions at hand.
I think that makes sense to me. Are there any other final questions?
Yeah, I had a couple of questions. So you mentioned Certic has been involved quite a lot in developing this, and I'm wondering, so how are they using it, or is it just an R&D project for them, or what's the connection?
I think it's best described as an R&D project for them. Yeah. If you look at their website, you get the impression that they want to use it for more than just R&D. But my understanding is that it's essentially just an R&D project at this stage.
Okay. And they're sort of pushing it to hopefully lead towards something that they could use.
Yeah, that's my impression. Yeah, I'd be happy to talk more offline.
Okay, yeah, fair enough. And just thinking about something simple like gas, can you use, DeepSEA to do gas analysis? Is that something that you could do, or does that not really make sense here?
Yes, no, it does make sense. So in fact, the DeepSEA code base does include gas analysis, quite strict gas analysis, all the way up to so imagine DeepSEA has lots of layers. Yeah. Right. So it goes all the way up, but the layer that we talked about today, which is the functional specification layer, it doesn't know about gas. But a couple of layers down, and it knows exactly how much gas you use.
Right.
Yeah.
Okay.
Yeah.
So I have a follow-up question, because you said you are not interested in EVM low-level code, but gas is at the EVM low-level code. So how can you reason about gas at the high level?
Yeah, it's so like I said, it's the high, for me, the high level is like we had with slide 16, like here, this one. So at this level here, where we have if then else threat 0, this level can't reason about gas. And then this is kind of one level down. I can't remember if it's this level that can reason about gas or just the one below it. But for me, I'm just more interested in this level. I mean, it's not impossible to make gas reasoning available at the top level in principle. I don't think. I just think it hasn't been done yet. But it would also add a bit of complexity, and it's a trade-off sometimes between, do we care about gas at the top level or not? Like we might overcomplicate things. It can be a trade-off, because a lot of the time, not all the time, but like for some contracts, the possibility of running out of gas doesn't really matter too much. But yeah, maybe I'm just too much of a theorist.
I'm not going to go into that one, I think. So look, thank you for your talk again. Can you flip over to those extra slides I had?
Yeah.
Do you have them available?
That's them?
Yeah, that's them. Okay, so let's talk about future talks that are coming up. So next week, we've got myself and Ermias, and we're talking about the cross-chain risk framework. So this is a open source available framework for analyzing bridges, and it's open for everyone to contribute to. And so we're going to give a talk about that and explain what it is and how you can get involved and why you might choose to use it. A week after that, we've got Zariaz, and he is going to talk about how Immutable are using zero-knowledge proofs to scale Ethereum and talk about their systems. We've got then Musa Abdeen to talk about his PhD topic, which is about blockchain and accounting. We've then got Roberto and Tan Hai coming up to talk about the distributed validator technology, formally verifying that. We've got Babu talking about MEV, and then we've got Barnabe Mono from Ethereum Foundation talking about proposer builder separation. And then at some point, it's probably actually not going to happen in March, I'll talk about assembler. Could you do the next slide, please? Okay, so the IEEE ICBC cross-chain workshop, its call for papers has been pushed out to, it's actually not January 23rd, it's next Monday. So February I believe it's the 6th. And so you've got another couple of days, another 3 or 4 days, 5 days to get your either academic paper or industry talk in. And then that will be the hard final deadline. So please put your papers in. It's going to be a hybrid event based on the Dubai time zone. And the next slide's the final one. Yeah, thank you. So if you're here today and you want to watch this again, please go to that YouTube channel. If you want to get involved in the discussion, go to that Slack workspace invitation. If you're watching this on YouTube and you want to be able to ask the speakers tricky questions live, join the meetup group and come along. Sometimes we have example code, and that's in that repo, and there's a formal methods reading group. And so to get involved in that, join that Slack workspace and then join the formal methods reading group channel within that Slack workspace. And that's all. So I guess, Daniel, we can stop sharing now, and so we can see everyone. And so thank you again for your time. That was really awesome. And so thank you for presenting today. And I guess we'll all give you a round of applause. So thank you. Yes. All right. Well, have a great week, everyone.
Peter, before you go, I was just going to say as well that this year at the ICBC, the IEEE ICBC cross-chain workshop, all accepted papers that are presented will actually, the academic track will be published as part of the larger ICBC conference in their conference proceedings. So it's a great opportunity as well for people who want to get some publications out and good peer reviews to submit a paper.
Yeah, thank you for adding that in. That's important. So yes, And as we all know, for all of us who've done PhDs, and even if you're still not doing your PhD, getting those academic papers out is super important. All right, talk to everyone later. Bye-bye.
Cool, thanks, Peter. Thanks, Daniel.
Thanks, Daniel. Thanks, Peter.
Thanks very much.
Bye.